So just to kind of pull up what we had yesterday, we had this same question, and all I really want to do is just have you kind of quickly look at it and recall the solutions we got for it. And I just want to show you kind of a different way of arriving at the same thing through something called the instantaneous center of rotation. And so let's see. So we got velocity of 5.89 for the velocity of C as it rotates around B. We got velocity of C, which was in the X direction of 12.08. And then we got the rotational velocity of that connecting rod from C to B. We got that as 0.59 radians per second. So let me introduce with the same exact problem today's approach to this. It's just really, it's kind of a beautiful thing. So in a sense, like we're going to do some more problems today like we did yesterday, in a sense, to try to help you get your mind around this, conceptualize it. But then now we're going to have kind of a second way of approaching it. And we'll sometimes use one, sometimes use the other. And on the test, I'm just going to kind of say, figure it out. And you can use whichever method you kind of end up liking. Yeah. So the idea is this. So this problem, again, looks identical. There's nothing different about it. But I want to introduce something called the ICR, instantaneous. What do we got? We got nothing. Dang it, user error once again. Instantaneous center of rotation. Thomas, can you see, is that green light blinking on that thing? Is it on its way to on? See a green light on it? Takes a minute for it to kind of heat up, but so ICR, and the idea is this, and let's just kind of do this problem with this question in mind. So we said yesterday, and this is good for your info, your knowledge, your brain power. We said that as far as B goes, rotating around A here, we're seeing it following that dotted circle as it cruises around. And we said that, well, in order for that thing to cruise, and we were told in this problem that the rotational speed, angular velocity, two ways of saying the same thing, was 2 radians a second. So we said this thing was going this way. Therefore, the velocity of B, we said yesterday, is going this direction. And remember, when you write it that way, that's a linear velocity. So at any given point in time, that's the direction you're facing. If you're a car going around a corner, your velocity is aiming where you are. Now your angle is turning, and so you're changing your direction. And we said that's an acceleration. That's an acceleration change, a direction change. Again, coincidentally, just yesterday I was doing my next flying lesson, and I was flying something called rectangles, which is kind of cool because when you're in an airport area, that's where all the planes are. You got to all act the same. You can't just like, hey, I'm going to go land over there. So there's a rectangular pattern that you kind of follow around. And of course, the air traffic controller, as people hop into that pattern, they have to ask permission to hop into the pattern. And the air traffic controller tries to get you to hop into that pattern in a way that, you're spaced between other people. And so, when you're in that pattern, then you'll cruise around and then land. And then the next person can cruise around and land. And so you're all at the same elevation, so you can see each other and not crash into each other. You're watching, they're watching, let's not run into each other. But it was super cool because what you got to learn how to do is basically fly in the shape of a rectangle. When you get to a corner, so you were flying yesterday, a rectangular field like this, so I'm flying along next to it. The runway's in the middle of that. I'm flying along like this, and you get to the end of this rectangle, you take this circular corner and you try to turn in such a way that now you're parallel to this corner as you fly along. And so, this idea here of, what's your velocity? Well, I had an airspeed velocity just because I turned the plane, didn't change that velocity necessarily. In what direction is that velocity going? Well, perpendicular to the the center around which you're rotating. Does that make sense? So in my case, that imaginary corner of the fuel right here that I was turning around, whatever distance I am right here away from, I want to, at this point, bam, there's this quarter circle that I try to fly in. What you don't want to do is screw that up, because if I turn super sharp, does it make sense I might end up like right next to this, and now I haven't kept that distance the same. So I'm trying to radius around that corner right there and tilt in such a fashion that I stay around it. So the entire time I'm turning the circle, but every time I'm changing direction, I'm velocity this way, and now it's this way, and now it's this way. And finally, I wings level, straighten out, and then flying along straight. So again, you should feel reasonably good about that. And of course, because that is being pulled in the counterclockwise direction, that of course is, we said, going to cause this thing to go in that direction as well. And so, cool. So what's the instantaneous center of rotation? How do you approach that? Well, these two things are, there's two things happening at the same time. Now watch this really closely because it's kind of cool. If I take off perpendicular to this velocity right here, I'm even going to fill that in so it kind of stands out. If I take off perpendicular to that, that would be here. That was a fail. Somewhere on this line. Now notice that went right through the, well, the center of the circle. But I guess what I want you to understand is where that velocity is right there, does it make sense to you that the center of the circle could have been here, and that still would have been the velocity, or the center of the circle could have been over here? Because all of those, it could have been right here. That velocity is perpendicular to any of those locations. I mean, the circle could have been centered at any one of those locations, other than the one it's actually at. And so, okay, great, fine. Well, if I cruise to that other location, get to the right spot.
That changes the normal acceleration, depending on where that radius is.
It changes the normal acceleration. Yeah, that's exactly right. Because if you turn a super sharp circle, you've got to really change your direction. Like flying, I'd have to lean way over if I wanted to carve a tiny radius circle. That's exactly right. So if I moved it further away, as I described there at the bottom, then I wouldn't have to turn. My normal acceleration would be much smaller. I would feel less of that, if you will. So, okay, that's cool. So in one sense, you could think that could be any one of those places. Now, here's the cool part. What if I went over to the other one and did the same thing? So I'm looking at this drawing, thinking it's suspect. This drawing is suspect for this example.
We're doing 51, which was what we did last time.
Yeah. So this is the same one we did last time. I'm just kind of showing you a different method for it. But I'm suddenly staring at it, kind of doubting it. Now, what happened?
The 61, 60 are a little different.
I was
Yeah. Oh, okay, got it.
well, thank you.
Yeah.
So do you agree that the velocity of C is going to go this direction? And it's stuck in that cylinder, if you will. So it's kind of heading that direction. It can't really go any other place than that. And so I could do the same thing with this. In other words, I could take off, well, I guess in this direction right here. Does it make sense that this being 90 degrees, I could consider, at least for that instant in time, does it make sense I could consider that the center of BC also rotating around a point? Now, is it going to rotate around that point? No, it's going to go straight. But at least for that moment in time, I could think, yeah, it could be that velocity of c right there could be actually rotating around this center right here, if I wanted to. Not only that, does it even have to be in that direction? Like, could it be over here? Notice the word instantaneous calculus. Like, this is only going to be true for an instant. So that velocity c could be rotating, could be thought of as rotating around either one of those centers because it's perpendicular to that, at least for that instant. And notice those two centers are not the same place. I'll go ahead and draw one in over here. That's the center. Like, those two centers are completely different locations. Here's where it gets interesting though. So as long as I take off from those two velocities perpendicular, I could kind of think of that center being any place I wanted to. Now, again, you should think, well, why would you do that? You know, this doesn't make any sense. What are we doing this for? Totally get that. But let's go back over this in blue now. What if I did this? I'll draw a few blue lines here. This is where I'm afraid this is going to go off the rail because it's not going to fit. I may have to draw this wonky. What if I drew that direction? Does it make sense, those two blues, like it could go that direction too? Would you agree that someplace where those meet up there in the air would be a center that worked for both of them at the same time? Now, again, that's kind of weird because it's this arbitrary location, right? It has nothing to do with the geometry of the picture and so forth. But what if I actually found the instantaneous center that they both rotated around at the exact same time? What would that do? What would that mean? What would that be like? Well, let's go, since I kind of have that on there in such a way that you can't see it, let's go ahead and draw that out. So I've got this going down here. I've got this going over here. And this goes up here. So I've got this triangle, and that's that instantaneous center of rotation. Now, again, you can picture that as soon as, remember, B is moving around the circle, right? As soon as it moves, then the center is in a new location. It's only the center at this instant. So that word instantaneous is really important. But like, who cares? What would that actually do? Well, here's this non-right triangle. Let's just think about, do I know anything about that non-right triangle? Well, notice I know phi. I was told the instant in time where all this went down, bam, the angular velocity, the instant when phi is 35 degrees. So that's 35 degrees. I know something about that. What else do I know?
Theta is 65.
Theta is 65.
With that right triangle, you have the 25 degrees.
So you're saying do something like this. And so your first thought is, I know 65 degrees, but that's not really in my triangle. So you're being creative and saying, well, if I made that 65, then this angle up here would be 25. Does that help me get into that triangle at all? Because I mean, if I could know this angle, that'd be kind of cool. Let's see, what else do I know here? I know this angle's 90, right? Does that help me? This angle here? Why do you say that? You're right. Because you have a parallel, and a line that cuts through it. So this angle and that angle ends up the same. So maybe you know that geometry concept, and there actually is a nerdy math name for it. Those are alternate interior angles. They alternate on either side of that line, and they're interior of those two parallel lines. Let me show you a more logical way to get to that if you don't sort of have that theorem, that geometry theorem in your mind. Let me change colors here. What if you drew this over to here, this down, like get some right triangles going? So if this angle phi here we said was 35, then since this angle down here is 90, then does that make that 55 degrees? And if that's 55 and this is 90, then that means this angle up here is 35. And so, hey, look, we got up there. by just using the fact that we know triangles add up to 180 degrees. Now, does that do me any good? Like, cool. Does that do me any good though? Answer is yes. Can you see it though?
You got 65 right there.
That's a straight line, right? And we basically broke it into 1, 2, 3 angles. That's a straight line, then it's 180 degrees, right? So if I know 25 and 35, which is 60, then that leftover question mark actually must be the remaining 120 degrees. So actually, I know a couple angles in that triangle up there. And now that I know those two, I know them all, right? Because the angles in a triangle are 180. So actually, I was able to figure out the angles in my cool triangle up there. Let's see, 135 or 120, 135 is 155. That leaves us 25 degrees short up there. I wonder if that's a coincidence. I'm not going to think about it, but I wonder if that's a coincidence that 25 up there happens to match the 25 we had earlier. Actually, I think that actually is worth our time. Is that a coincidence? It's actually not, because I'll erase this, but if I drew a line straight down here and I continued this line right there, and this angle right here, as we said over there, is 25 degrees, then since this line right here is a straight line and this jumps straight down and that's 25, this also comes straight down. So those two would have to match each other. So that actually wasn't a coincidence. Perhaps that was a way I could have got into that other triangle. So you just got to take your time a little bit, draw triangles, draw right triangles in, but you can actually use the angles that you know to kind of figure out what's going on in this cool triangle that seems to have nothing to do with this problem at this point. So in terms of your knowledge of trigonometry, what do you got to know about a triangle to kind of figure stuff out about it? I know all 3 angles. Do I know any lengths? Yeah. CB was part of the mechanical structure of this. Somebody made the connecting rod from C to B 10 meters. We were told that up here. So that's 10 meters. And what it takes to know, because triangles are made of 6 things, 3 angles, 3 sides, you got to know 3. And unfortunately, it's a certain 3. If you know 3 angles, that doesn't do it, because there's tiny triangles with those angles and there's big ones. And so a certain 3. If you know 1 side and you know 2 angles, bam. You know 2 sides, 1 angle, bam. All 3 sides, bam. But now that I know this, does it make sense I can use the law of sines and cosines to figure out those 2 missing sides? And again, notice those 2 missing sides in our actual problem here are kind of these weird, irrelevant. They sort of feel like, why would I want to know those 2 lengths? Like they're around some center that isn't even part of this problem. And not only that, when 1/1000th of a second goes by, that center is going to move to some other location, right? In the interest of time, I will stick this in my side angle program that's in my calculator. Save us time. So I'm going to stick in the angle just so that we're not doing, oh, geez, I don't even have that program in here. That's not good. I guess I'm not going to do that. It's in some other calculator. Let's see. I want to figure out. So that's okay. This is good for us anyway. This is dangerous, what I'm about to do right here. In terms of your understanding of trigonometry, it's way better to figure out this side next. Because what I'm going to do is the law of sines. I'm going to say, oh, the sine of 25 divided by the side across from it will be the same as the sine of 35 divided by the side across from it. Actually, this isn't dangerous because if you don't know an angle, it's dangerous. But if you know the side, then you're trying to find the side, then you're fine. So actually, this doesn't matter what side I would have figured out. Now, just based on proportions, 35 degrees is bigger than 25. Therefore, it's open wider. So I should get something more than 10. Hopefully that makes sense. So if I take 10 times the sine of 35 And divide that by the sine of 25, I get 13.57. And I'll call that y. Go ahead and write out the same thing. The sine of 25 divided by 10 would be the same as the sine of 120. This is the biggest angle, so that should be the biggest side. So it's the same exact setup. I just got to take the sine of 120. And when I do that, I get 20.49. So I know those two lengths now. And since those were meters, since 10 was in meters, those are meters as well. So cool. Need to keep track of those, but it's like, who cares? Like, what does that actually have to do with? Here's the cool part. So I'm going to just call this I up here, and we have names for the other 2 points, C and B. And I want you to think about this. Fact. The angular velocity of IC, or I as it rotates around C. No, I said that backwards. Do you agree with that? Do you agree that I said that backwards? It's C as it rotates around I, because remember, I is the center of rotation. So it's the center. It's the corner of the rectangle that I just flew around a second ago. It's not doing the moving. I is sitting still, and C we said was actually moving. And I think this is important to draw in. C was actually kind of flying in that direction to the right. The fact is that will actually exactly equal the rotational speed of B as it rotates around I. And we said B was actually going that way. Again, those are perpendicular. So watch what I erase here, and then I'll put it back. But in a sense, I don't really care about that line right there. I really am just looking at those two radiuses and velocities. Now, the only reason I drew that other line is because the geometry that created, creating a triangle, allowed me to find the two radiuses. You see what I'm saying? I now know the radius of those two rotations. So we said, this is the velocity of C, this is the velocity of B. Now, because we did the geometry to actually find a center that worked for both of them at the same time, the question is, can you wrap your mind around that fact right there? That those two rotational speeds, again, your book would call those angular velocities, but rotational speed, those two would be identical, at least for that instant. Now, why is that? It's because they're connected to each other. So watch this notebook. These two views of the notebook have to rotate at the same speed. Well, the answer is no. I could have this one go really slow, or this one goes really fast. Right? But I'll look at my body, for instance. So if I'm standing here like this, and I decide I'm going to rotate, in other words, I'm fixed. Now, if I wanted to, I could rotate this arm at a totally different rate from this arm. But if they were fixed, in that triangle right there, that blue triangle, it's fixed. Stuck, at least at that moment, it's stuck right there. But if I rotate like this, every part of me is rotating at the same speed, right? My nose is not very far away from the center of rotation, although my nose is big and longer than most people's. But my elbow's pretty far away. And so this one has a faster velocity. Does that make sense? The elbow has a faster velocity, linear velocity, but the angular velocity of all parts of me are moving at the same exact speed. And so they're kind of locked in that triangle right there. So it's kind of like you're spinning a triangle, spinning a piece of paper on a table or something like this. All parts of that are rotating at the same speed because they're connected, at least for that instant.
So that means.
Now, one instant later, it's a different rectangle or a different triangle. Does that make sense? And so
But
that's
the
what's kind
degrees
of.
are changing at the same rate when we go to that next instant in time.
So, yeah, I mean, in a sense, what this allows us to do, at least at this instant, is say, hey, if I know the rotational speed of one of those, I can jump to the other one. So let's consider that for a second while you kind of get your mind around this concept. And remember the other fact that we have been using the last couple of days, that the linear velocity of something is equal to the angular velocity as long as you multiply the angular velocity times whatever the radius is. Okay, so let's consider kind of what's going on for that IB situation. Again, think of B as like an airplane flying around a point. What's going on with that guy? I won't recalc it, but we said yesterday, if I remember, that that was 8. I'm just kind of using my, we took the time to, yeah, we calculated the velocity of B was 8. Yeah, because it was, and it's probably worth rethinking, but let's take a quick look. This rotation right here was 2 radians a second. Notice that's around a totally different point. And this radius was 4. And so radius of 4, distance of 2, those get multiplied. Hey, look, that linear velocity is 8. So that was kind of known for us, if you will. So we said that was 8. Now, again, be careful because it's like, do you understand I can't put 2 here? Because we're talking about it rotating around I, not around A. This is a totally different location, so it's not 2. But don't I know the radius thanks to that X calculation I made just a minute ago around I, because this is I rotating around, or B rotating around I. So we just figured out that X value is 13.57. So I can say, hence, if I take 18 divided by 13.57, 8 divided by 13.57 is 0.59. That would be the rotational speed of B as it rotates around I. Well, what's going on over there at the other one? What about what's going on with IC, the other airplane that's in the same exact picture, so to speak? What is its velocity? What is its angular speed? What is its radius? Well, we figured its radius out. We said that was y, that's 20.49. But remember, its velocity is velocity of C, which was one of the things we were trying to figure out. That's one of the things we were being asked to find here, right? Find the velocity of C. We were told that was like one of the first things we wanted to figure out. Find the velocity of C. Well, does it make sense since we said that these two angular velocities are the same, that I can take that angular velocity there and plug it in here, and I'll know the velocity of C then. Maybe I'll go to the trouble to even write C there. It's the velocity of C, and in the previous one, that was the velocity of B. Oh, so if I take that 0.59 number and multiply by 20.49, I just got that the velocity of C equals 12.08. And because this was metric, that'd be meters per second. Like I just worked my way over to one of the answers that I wanted to know. Velocity of C is 12.08. Now, take a look at yesterday. Wasn't that one of our conclusions? There it is, velocity of C, 12.08. Hey. Now, what did we have to do to get that yesterday? Well, we had to use this fairly complex equation that we're not feeling too good about yet, right? And then we had to write an equation in terms of X and in terms of Y. In my particular, the way I happened to do this. In my case, I wrote an equation in X and it had two unknowns in it. And then we switched to the equation in Y and realized, oh, it only has one unknown. And we found this velocity, and then we were able to plug it back in the original one. We had a lot of work to do to get 12.08 is kind of my thought, my concept here. Isn't it weird that we can get this with the concept of the instantaneous center of rotation? So this is kind of neat. And now, is it always easier? I don't know. I mean, it's less work. It took geometry to get that answer but again, notice how different this is. I mean, that's a crazy equation there. You can't not know that because we got other things to talk about and so forth. You can't go, sweet, let's get rid of that. I can get 12 in another way. But again, I kind of highlight who's the genius who thought of that idea. It's one thing that for us to follow it in somebody's footsteps, but it's like, wow, that's just crazy that somebody figured that out. That's the concept of the instantaneous center of rotation. If you can find a center that's perpendicular, let me just highlight that again, because we're going to go do another example. If I can take off from one velocity perpendicular in whatever direction I want, a center of rotation, any place on that line could be considered, some instantaneous center. But if I can do it from the other one as well, go in any direction I want. Notice my initial thought was to go, well, down, but in the end, to get them to hit, I had to kind of go up off the page in this case. And that allowed me to find that instantaneous center and do some trigonometry and actually get the same answer I got before. Let's see if we can pull this off with a brand new question. So I want you to stare at this for a second and see if you can tell me where that instantaneous center of rotation would be. Actually, let's do 61 first because it's different. This is the drive. This time the piston is the driver. So notice it's going to the left. Awesome.
Did that not matter in this last example, what the driver was?
Nope, doesn't matter. Yeah. But all I wanted to do is just do one that looked different. So it isn't going to make any difference. No, it makes no difference whatsoever. I just didn't want it to look exactly the same as we just did, frankly, so that you can get comfortable with exactly what you just said. My question is, what's happening to B? B is following that dotted line, but the question is it going up and to the right or down and to the left based on what you see happening at A? You should be able to answer that just based on logic. Yeah, it's going to cause B to have to go down, and therefore it's basically going in this direction. So again, can you accurately draw in the velocity of B? What direction is the velocity of B going? And in order to draw that, what are you thinking when you draw that? I'm asking you to read my mind, I know, but perpendicular, exactly right. Perpendicular to BC, that crank arm, that's what you're thinking in order to get it to look right. In other words, when you come up here, you don't just kind of go, well, it's kind of going that way. I mean, like try to make it 90 degrees because that'll help your math. So yeah, I'm taking off at 90 degrees. Doesn't have to be perfect, but just get it close. So that would be the velocity of B. So I'm going to go darken this in over here. So you've got the velocity of A, which you actually know. And so what do we got to do to find the instantaneous center? We got to take off from those two red vectors perpendicular and see where those run into each other. Can you visualize where that would be? So here I am taking off from this one perpendicularly. I'm going to fill it in. Bam, bam, bam. I'm going this way somewhere. Be good to have a ruler somewhere down there, or it could go up. What am I doing with the other one? Again, what am I taking off perpendicular to? That velocity is what I'm taking off perpendicular to, which is the radius of that circle. So bam, 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 bam. Aha, look at that. They ran into each other. Good news, my friends. We just found the instantaneous center of rotation. I'm just going to call it I this time. ICR or I. At that instant right there, that imaginary center that has nothing to do with this picture, it's nowhere in the machinery. If I can find those two dotted radiuses, given the fact that at that moment, this kind of fixed triangle ABC, I'm sorry, ABI, this fixed triangle that exists for at least just that instant in time is going to cause the rotational speed of A as it rotates around I and B as it rotates around I to be identical. So if I can find those two distances, those two radiuses, that's what's going to connect 5 to velocity of B. I'm just going to be able to go straight to the velocity of B, thanks to all this geometry. All right, so now we just got to attack that triangle AIB. We got to say, all right, I got to know some stuff about that thing. I got to know enough to bust into the law of sines and law of cosines. That'll very seldom, if ever, be a right triangle. So it'll be law of sines and law of cosines. And when I make these problems up, I'll make sure that the instantaneous center of rotation is actually on the paper like this one is, instead of, blowing off the page like the other one did. So I'm told AB is 6 feet. So that's worth throwing in there. So I know one side. And then I know all these angles. Well, phi, I'm told, is 38. See the right triangle up there? If that's 38, doesn't that make this angle in the triangle 52? It's like I'm on my way. This is going good. All kinds of things you could do here. Let me show you something rather creative though this time. It's not hard, but just make your life a little easier. So that theta angle up there is 32 degrees and it's taking off straight from here. Well, what if I came down here and took off straight from there just like above? Then if that angle up top is 32, isn't this one right here also 32? This is like parking places. If you have a parking lot, it ends up looking like that. Aren't all these angles right here the same angle? They're all parallel to each other. They'd all be the same angle. Isn't that kind of what I just drew? Like, that's kind of a nice way to get over there, to get involved. There's literally a dozen things you could do to figure this out. Some will be fast and easy and some will be slow. Who cares? Just get it figured out. Slow down, draw pictures, draw right triangles. Now, did that do me any good though? Because that isn't even in the triangle. Yeah, because this angle right here is 90 degrees. Because this angle right here is 90 degrees, 32 and 58. So there. I know two angles and I know a side. And so now I can switch to law of cosines and figure stuff out. And I could add 52 and 58 and get 110, which means this angle up here must be 70 degrees. In case I need that for something, I probably will. Sweet. So I think I'll use the angles in the picture this time. So I can say I'm picking the angle on the side that I know. So if I say the sine of 58 degrees divided by the side across from it, which is 6 feet, that'd be the same as the sine of any other. So I'll say the sine of 52 divided by the side across from it. Instead of giving it a new name this time, I'm just going to call it IB, the length IB. And while I'm at it, why don't I just keep going, which also must equal the sine of 70 divided by the side across from it, which is IA or AI. So that's what law of sine says. Oh, cool. That means I can find any of those I want. 6 sine of 52 divided by the sine of 58. And it's easy to push buttons wrong, or, I'm trying to kind of do the algebra in my head, but 52 is smaller than 58. So the side across from 52, IB, better be smaller than 6. but 52 is really close to 58, so it shouldn't be very much smaller. And I got 5.575. I'll just call it 5.78, close enough. So that's very logical. Very close angles, very close lengths. If that had came out 3.2, I should have questioned that. Like, what? There's no way it's that much smaller. Or if it came out bigger than 6, no, there's no way. Something's wrong. 70 is my biggest angle. So if I use 70, I should get something more than 6. I got 6.65. Sounds good, I guess. So I now know those two radiuses. Just so that it's easier to see the logic of all of this, I'm going to go write them in where they belong. This is 6.65. That will not do. 6.65 feet. We said IB was 5.78. Do you notice those are both rotating in the same direction? Those two vectors, those red vectors up there, they're both causing this whole triangle, if you will. Again, think of it as like a solid triangle made out of steel or something. At least for this instant, that solid triangle, kids on a merry-go-round, they're rotating around I, but notice they're going the same direction. Does it make sense it would be impossible for this one to be going that direction? If those are 2 points on a fixed triangle, they can't go different directions, right? They can't go toward each other, at least if the triangle's fixed or solid. So they're going the same way. They're rotating in the same direction. Sweet. So this is going to allow me, and let's do this one a little more, I don't know, algebraically. We said a second ago, it's the kind of thing that Caesar would like. We said a second ago that, you know, velocity is angular velocity, linear velocity is angular velocity times radius, which means I could rewrite this as angular velocity equals linear velocity over r. And since we said those two angular velocities are equal, does it make sense that I could just write then that the linear velocity of 5 feet per second, divided by its radius, which is 6.65, would have to equal the linear velocity of the other one divided by its radius? Does it make sense? I could do it like that if I wanted to. Last time I just went a little slower and used that formula twice.
So if A did not have a velocity, this method wouldn't work.
Yeah, you got to know one. In other words, what we're trying to do is move, in our case, we're trying to move from the fact that we know one velocity over here at A, we know what the piston's doing. The explosion has happened in the engine, and now that piston's moving. And then because there's a connecting rod between those two, then we want to say, well, what effect does that have over on the other one where rotational speed is being developed?
We can't use this when the piston's at its apex or at the bottom of the cylinder when it's.
No, you can use it anywhere. Oh, I see what you're saying. You're saying like, what if it was up here? Because that would be the velocity of B. Does it make sense if I tried to draw this line down that these would never run into each other? So yeah, there actually are a couple of places where at least for an instant it doesn't work. I don't know if that's what you were getting at, but it's, if you weren't, just say, yeah, that's what I was getting at, because that's a great question. Take credit for it.
Yes.
So if you don't blow that, you get the velocity of B. And notice the proportion. 5 is to 6.65. Well, 5.78 is less, so I'd expect the velocity of B then to be smaller. And sure enough, when you punch buttons, you get like 4.33 for that, approximately. So I'm going to recalc that. .35 actually. And again, we might as well not be lazy about units. This was all in feet and inches and so forth, feet and inches and seconds. So I just got straight over to that velocity without that crazy equation we had earlier. It's just kind of weird that it's possible. Now, again, that did not take as much paper. It did not take as much brain power. I'm a little bit inclined to think this method's a little faster, a little bit easier. So it's like geometry that allowed us to jump from one to the other. And just to highlight what we said before, the key is really that at this instant, and I might say, you know, that instant right there, we can say that the angular velocity of A as it rotates around I will match the angular velocity of B as it rotates around I, thinking of that triangle as fixed. This all hangs on that principle. Now, if that's all we needed to know, we're done. But notice it said using the concept of the ICR, find the angular velocity of link BC, not the angular velocity of BI, because I isn't a thing. Like I is not really actually a part of this. But could we find the angular velocity of BC? B as it rotates around C. Is there some way we could figure that out? Who's got an idea?
That velocity divided by BC. Or, yeah,
Like this stuff? Is that what you're saying?
Yeah.
That's exactly right. Like, don't I know a linear velocity of B? And notice that linear velocity doesn't know about a radius. It doesn't know what radius it's at. It's just a linear velocity. I'm flying around the plane. I look down at my speedometer. I'm driving around the corner. I just look down at my speedometer. It doesn't know what the radius is. That's a separate issue. That's exactly right. I know that B equals angular velocity times radius. But notice, because we're being asked for the velocity of B around C, that means this radius is also C around B, or CB. And in this problem, I was told that was 2 feet. So does it bother you that it's not 5.78? Like, didn't we just find the radius is 5.78 a minute ago? Well, that's true. That would be the angular velocity of B as it rotates around I. But that's a much bigger sweep, if you will. I wonder if we'll get the same answer. Notice in our previous calculation, we never even figured out what that angular velocity was. And the only reason I didn't figure it out is because it isn't even real. Like, it's not a part of the actual problem. Do you see why somebody wouldn't care to know what the angular velocity around some point that has nothing to do with the mechanism is? But somebody would say, well, I would like to know how it's rotating around C, because that actually is part of the motor, right? That's what turns the wheel. So I know my linear velocity of B, and notice that, again, that's okay. It's not like that one's okay. That's useful. Oh, okay, so if I take 4.35 and divide by 2, which makes it 2.17. So this would be angular velocity of B as it rotates around C. And because it's angular velocity, that would be radians per second. Again, I'm being a little lazy, but remember 4.35 was feet per second. If I divide feet per second by feet, I get nothings per second. So this unit has to be radians. That's just kind of cool. And so I've accomplished everything that we did yesterday now, but it only took me half the page to do it. And I think less brain cells, at least for me. I'm in less pain than I was yesterday from this process. So don't lose sight of the goal. The goal is, I'm over here and I know what's happening there because that's the driver. I see that it's working its way left, apparently at a constant speed of 5, because there's no acceleration given. But there's this connecting rod over here that's connected to something, and that something is in a mechanism that's causing it to go in circles. And so since it's connected, it's like, wouldn't there be some way to get from what's happening over here through that rod to what's happening over here? And the answer is, yeah, look at that. We got the velocity over there, and we even have the angular velocity of what's happening over there. It's like I own the way this engine's working. Now, as I said, the downside of this is it'd be kind of fun to make some kind of a Desmos for this, because remember, all of this work was only for that instant in time. If we let a little time go by, does it make sense that these two angles right here are going to change? And I'm talking like 1 second. And for a motor that, you know, rotates at 3,000 RPMs, it's like even 0.1 seconds is a lot of time. It's like pollen. So if I move that a little bit, I'm going to get a totally different answer for all of this. So it'd be kind of fun to create some kind of a Desmos where you can sort of just locate. You can almost like physically grab A and just kind of move it to a new location, and it would just tell you what's happening on the other one. Maybe a spreadsheet that just listed all of them, like for every angle, if you will, something of that nature. But it's just cool, at least, that you can get over there mathematically. Why don't you try to make a little progress with this yourself before I do it. So this one is reversed in the sense that the driver here is 3 radians a second. So AB is rotating at a constant speed of 3 radians a second. So B is doing the moving, and then C is going to follow behind it as a result. So can you draw in your 2 velocity vectors and then draw perpendicular lines to those and locate the ICR, and then start calculating all the radiuses and so forth? Notice I said 3 radians is counterclockwise. That is very important here. I was just looking at 3 and thinking it was positive, but then I read the rest of the question. As a result, that means C is actually going to travel downwards. Double check and see if you got the ICR, the instantaneous center, kind of over there in the right general area. Again, I think it's extremely helpful to draw in those two red vectors, draw in some 90-degree angles. It's kind of cool that the connecting rod from C to B is in the triangle because that's what connects these two motions. That's why this is called relative motion analysis. One is made relative to the other based on that CB connecting rod. Hopefully you notice the angles in this one are much nicer, like in terms of jumping into the problem, since phi is 24 degrees and I've got that 90-degree angle down there. Hopefully you saw that, oh, that just means 24 and 90, that'd be 66 degrees just sitting right there for me. And then this angle theta up here is 40 degrees and the one down below it is in the same exact location. So that'd also be 40 degrees. Hopefully you saw that. Like, oh, that wasn't too bad.
Simple arithmetic.
And then 40 and 66 is 106, which leaves 74 for that angle at the upper corner. And since I know the connecting arm CB is 56 millimeters. Notice that's sort of insanely small. Millimeters, isn't like 0.5 centimeters. This is like half a centimeter. This is like a watch or something. This is teeny. But the one thing about this is I don't know either velocity this time. I don't know velocity of B or the velocity of C. You got to know one to get to the other one. But remember, the trick to that is the fact that, well, I do know that rotational speed right there. And since velocity is equal to rotational speed times radius, then if I know that rotational speed is 3, and I know the radius of the crank arm AB is 17, then that means that velocity is actually 51. Notice though, if you leave 17 alone, you have 17 millimeters times 3 nothings per second. This is actually millimeters per second. So, part of me thinks we should turn that into meters because meters per second. The other part of me says it's a watch, man. Don't call it meters per second. It's really tiny. Doesn't matter. Just like, don't lose track of that. So that's a speed. So I actually do know one of the speeds thanks to the rotational speed. So back to the law of sines, the sine of any angle divided by the side across from it will be the same as the sine of any other angle divided by the side across from it. So if I don't blow that, I get that BI is approximately 79.59. And I might as well not be lazy. Those are millimeters. $83.75. CI. And as always, I take stock. I stare at this for a second and say, okay, I could have pushed buttons wrong. My calculator could be in the wrong mode. I could have missed a number, anything. So our big angles across from big sides. My biggest angle is 74 degrees. Across from it is 83. That's the biggest side. My smallest is 56. It's across from 40. My medium size side, 79, is across from my medium sized angle, 66. Okay, this is looking good. That's the backbone of what the law of sine says. It's not the angle divided by the side. It's the sine of the angle divided by the side, but that's a statement that big angles are going to be across from big sides. It makes total sense. Open up the angle wider, the side across from it's going to get wider. So no guarantees that it didn't screw up, but at least it looks right. Since the angular velocity of B as it rotates around I is going to match the angular velocity of C as it rotates around I, then I can say and the fact that V equals the angular velocity times R, I can say that the velocity of B divided by the radius of BI is going to have to match the velocity of C divided by the radius of CI. And start plugging and chugging, as is often said. Velocity of B, I know, is 51. That radius of BI, I know, is 79.59. And the radius of CI, I know, is 83.75. Oh, cool. I can find the velocity of C then. 83.75 times 51 divided by 79.59. 53.67. And this is a velocity, and I've kept it in my mind, but I haven't written it down. This speed is in meters per second. Millimeters per second. And it should not escape your notice to the point that Thomas made earlier, that this problem had a totally different driver. This time it was the crank arm AB that was doing the driving, and yet all this math we just did, didn't even notice. I didn't even notice that happened. I got a triangle, I got a couple velocities, didn't even notice. And notice this problem just asked for that velocity. I'm done. And of course it did, because is there an angular velocity down there at C? Nope, because it's a piston. This is a circular electric motor, if you will, that's driving this. Again, and maybe a watch is a good example. A little circular electric motor. And as a result of the fact that B goes round and around and around in circles, I wonder if you can visualize, as I showed you in Desmos the other day, that this C is actually just going up and down, back and forth. It's like you're taking rotational motion and you're causing it to go back and forth. Can you think of any inventions? I don't have anything in mind when I say this, but can you think of any inventions where you want something to kind of move that way? You need it to move back and forth, back and forth. I like a metronome is doing that, right? And it's kind of circular in a sense. I'm thinking of something like sweeping, like it's like sweeping something off, almost like a windshield wiper, except the windshield wiper is not, you know, it's angular, right? But it's like if I need something to do a job where something is moving back and forth, some kind of a machine moving back and forth like that. I'm wondering, did we see anything like that in the mill? Yeah, I mean, one of the things I saw was the beam kind of came over and then it was like, got it against the wall, and then it went through a saw, and so it was like, you know, in the end, that it's like something drops, it goes under the beam, comes back up, you know, but it's like, and again, one of the easiest things we can create is circular motion thanks to electricity. So it's like, in this way, I can take an electric motor and through a mechanism that connects it, a connecting rod like this, I could cause something to move back and forth. And so that's what's going to happen here as a result of that. I get that thing rotating at 3 radians a second. Notice that's like half a lap a second. 3.14 would be half a lap. So it's like half a lap a second. So just by virtue of controlling the speed of that motor, I could control the speed of how this is working over here. But remember, that's just at that one instant. Different instance, that's not a constant speed over there. So that's kind of fascinating.
I don't know how to say this like perfectly, but so the linear velocity and the angular velocity remain constant, like while one decreases, the other increases, etc.
You start trying to figure out the relationship between the two of them. I'm just thinking out loud here, but looking at that crank arm up there, if I draw a circle down here, and let's put B over in this location right here. So B is right over here and C is over here, and they're connected by this rod. Does it make sense if B goes a little bit this way or a little bit this way? C isn't moving very much. So in that location right there, if B is still moving at 3 radians a second, but what's C doing? Moving really slow, right around there. It's really slow. Where does B get really fast? Or where does C get really fast? Right there. So when B is here, this is going to be like slow C. But what about B is right there? Now what's right there? Why did I go there for B? Well, same thing, it's connected to C, but does it make sense? A slight movement here is in the same exact direction that C is going. In other words, if B was traveling in this direction at 4, does it make sense? C is right behind it, like almost like a trailer behind a boat. So it's also going to be going 4 right there. So over here in this location, this would cause C to move rather fast in that particular location. So as it cruises around, basically what's going to happen then is if B starts right, let's say B starts here and it works its way over to here. Does it make sense? C is just going to go faster and faster and faster and faster. And right here will actually be the max speed C actually goes. And then when it drops off here, then it's going to slow down until it gets right here. So these are the two slow locations for C. So it's going to slow down until it reaches a maximum slowness, I guess a minimum speed. And then it's going to pick back up again until it reaches another maximum right over there.
So whatever, the follower will have a period of fast and a period of slow.
That's exactly right.
The driver will be consistent.
Yeah, so the driver's got a consistent speed. And then that C, the follower in this case, is going to have a minimum speed and a maximum speed. And it's going to go from minimum to maximum, back to minimum, back to maximum, back to minimum, and just kind of keep doing that the whole time. So in terms of your machine, this is not going to go, this is going the same speed all the time. It's actually going to, be in one location. It's going to be going really fast and it's going to kind of slow down and it's going to go really fast. And, which if it was sweeping something off, maybe I wouldn't care, right? Maybe it doesn't hurt anything. Maybe there are some things that would hurt. I wouldn't want it to do that. I'd want to try to minimize that. Maybe if I made the circle smaller, that would change the way those speeds work. Maybe if I made it way bigger, maybe that would exacerbate the speed changes. I think it would. It's off the top of my head. If the circle's bigger, it's going to exacerbate the speed changes of C, the horizontal mover. If it's tiny, maybe it stays about the same, or maybe it doesn't make any difference at all. Obviously, the length of the crank arm would be, or the size of the circle, if you had a teeny circle, does it make sense that would cause the other one to not move very much? You had a giant circle and it's going to go all the way across. So interesting. All right. So in one sense, you didn't have to learn anything new today. Now, I would like to just say going out the door with respect to what we're going to talk about on Tuesday. Oops, that's the wrong class. I guess I don't have it in there. But look at the sheet I gave you. That's, I think the first one was 100 or something. I was going to bring it up, but I guess I can't. What do you notice that's different about that problem? So 100, it's down at the bottom, it says C's speed is 5 meters a second, but it also says that C's acceleration is 2 meters a second. So we're going to give it some acceleration. We're going to say C isn't just moving at a constant speed. And you may be able to appreciate in a car piston, if you basically say boom and it explodes and then the piston starts moving, does it make sense? It's going to move really fast at the start, but the power's been lost. So it's actually going to slow down from then on. So it's going to have a deceleration. It's going to have kind of an instant really fast, but then it's going to slow down from there until one of the other pistons kind of helps push it along. So a car does not have a constant velocity. Now, as I said, an electric motor would probably have a constant velocity as it spun around. And so great, no acceleration. Unfortunately, if that C has an acceleration, then that means the rotational speed and the other velocity is also going to have an acceleration, right? So what are we going to have to do to figure that out? Unfortunately, it turns out to be really painful. We basically have to do what we did today, which is say, oh, okay, the velocity right now is 5. So what's the velocity in the other location? Great. Okay, we got that. But now, how do we get the acceleration over there? Well, unfortunately, that's going to involve tangential and normal accelerations because we're talking about circular motion here. So we have tangential accelerations, which actually change the speed. But then we also have normal accelerations, which change the way the angle's working. And so we're going to have to write an equation in X and an equation in Y. Woo!
We have to convert our angular momentum, angular speed to acceleration, or angular acceleration, or angular velocity to angular acceleration.
That's
So
right.
we have to take integral to do that?
No, we'll be able to make a conversion because it's just like we took the angular velocity, multiplied it by the radius, and that gave us the linear velocity. We have a formula that converts.
Velocity squared.
Yeah, that's exactly right. I'll pull that up just since you brought it up, and it's right in front of me. Yeah, these two formulas right here. So notice as far as tangential acceleration, which is actually a speed change, you just multiply by the angular acceleration times r, so it's identical to velocity. But normal acceleration, in other words, a change of direction. And again, make sure you're visualizing this. It's like I'm flying my plane right here. And when I go around this corner, I am changing my direction. I have a normal acceleration change because I'm saying, let's fly over here. And I don't feel that. I'm getting pulled to the outside of the plane. But can't I also just push the accelerator? Let's go faster. And so now I'm not only changing direction, but I'm going faster and faster as I go around that corner. I can control both of those independently. AN is a direction change. AT is a speed change. So yeah, I'm gonna need those formulas. Notice I kind of have two choices here. For normal acceleration, I can take the angular speed and square it times the radius, or I can just take that linear speed that we figured out a while ago and just square it and divide by the radius.
Well, I don't see how we could then get AT unless we know. A.
Well, notice in that problem I just referenced that I couldn't pull up, I said the acceleration of C is 2.
Oh,
That's AT. Like I gave you one of them. And so we can turn that into an angular velocity. So you have to know something about one of them. But then the key is if I know something about one of them, then can I, through the connecting rod, can I get it over to the other one so that I know what's happening over there too? Yeah. It's really cool, but it does create a fairly large, painful set of equations. Since there's two forms of acceleration, we have to get into them. So again, my advice to you is come back to class with the velocity problems done so that isn't holding you up, because we basically have to get that before we can even start on acceleration.